right, welcome back. Last day of the week. Today we're going to do something a little different in that we're not going to look at any new techniques. We're going to apply yesterday's techniques to some problem solving related rates. So we've got a few examples to look at, but there's really, as far as taking a derivative, there is nothing new except more practice. A little bit, we'll identify some things, but we're going to be using implicit differentiation. Okay, so we'll use what we supposedly learn on Wednesday, or at least we talked about. I won't say we've learned it yet, but that's where all the techniques come from. Okay, so in a way, today will help anything maybe you didn't understand real clearly on Wednesday, now that as we apply it in some concrete settings, that it might make better sense. Okay, so the other thing I want to highlight, because sometimes I forget about these things too, is that remember the Canvas shell is from an online course, so there are a lot of videos in here. Where are we? Here we are, 2.7, that's what we're going to do today. And the reason I looked at them, and there was one other example I was going to do on a sphere, but then when I got looking in here, there's a really good example right here. It's a 4-minute example. I couldn't really improve on it. There is one on the sphere that is in your homework, so this will be a helpful example to take a look at, but it allowed me to do some others that aren't recorded here. So we'll look at a few examples, and but remember that there's these example problems here. There's also these full lectures done by Jay Abramson, and so you might find those beneficial too. I kind of like his videos. He brings in a student to make it feel like he's in a class. So he's in the studio, but he's always at least talking to a supposed student who's probably not learning it, but probably a TA. But anyway, they're kind of interesting. He does a good job. So today, let's go ahead and take a look again, sort of at where we're at. We're 2.7 related rates. So it's Friday. Next week, Monday, we hit 2.8. I don't know, I look at them the day or two in advance. And then we've got this review, okay, review of chapter 2. So it's kind of a time to kind of regroup, slow down, bring in any homework type questions. I did post the exam review. It's all available on that Math 265 on the department site, but I brought it over there. The one thing that's a little distracting, I think, is that each problem, they actually put in red the answers after each question. So for me, if I see the answer that it's harder to work through it, I would prefer to move it to the end, but it's a PDF, and I thought, well, let me just at least get it posted. We'll see. Because I think last time they had all the answers at the end, which is kind of my preferred way to do it. But when you do, just kind of put a red filter on your screen so you don't see anything red, and you won't see those answers. But we'll use some of those to get ready, and then again, then we'll go back into chapter 3. We'll cover that content. We'll do a review on it, and then we've got a review to bring everything together. So it's a little bit slower pace, a little bit more opportunity to stay on track. Currently, I have all the homework at least through 2.7 due next Wednesday for the review day. Just to let you know, I will move that. I kind of put it there just so that if those who are focusing on due dates try to get it done by Wednesday. But again, I want you to be able to work in them, because the way this web work works is once the due date hits, it shows you the answers and you can't work on them anymore. So we do want you to get through it. We want you to be able to go back and review that way, but I also want to have enough time. So I'll push it through to the Sunday, and then we'll get into chapter 3, and if you need an individual extension or something, let me know, and we can make that happen. Okay, so first of all, we're going to take a look at an animation. we're going to look, as we see this, as sort of something's animating, try to see this situation. And I guess I set it up for you. It's a ladder sliding down the wall. So think about what variables are involved here, what are possible variables, and what things are constant, because that's how we're going to be setting things up. And then I'm giving you a little bit that there are going to be 2 explicit variables and 1 implied variable, which might be kind of thought of as a hidden variable. And this is the hardest part of this part on related rates, is that you have to look at a situation and you have to set it up. Taking the derivatives, once you get it set up correctly, that's not probably going to be that much of a problem, hopefully. That we can work on. But how to set these up is because they're going to be so diverse. So let's go ahead and take a look at this animation. Let's see. It's going a little bit slower than it did earlier. So this ladder is sliding down the wall, and you can kind of see the time in seconds up at the top. It's kind of hard to read, but it's telling us that it's a 10-foot ladder. It's moving away from the wall at a speed of 1 foot per second. So the x, it's moving along maybe I shouldn't have said that. But anyway, the base, the floor, it's a constant rate. But what looks like, the other thing. So what are some of the variables involved here? What are the 2 implied or explicit variables that you can see there? X and y. And what is x and y? What do they mean? What does x mean? What does x measure?
The distance from the origin point A.
Okay, the distance, so on the base of the ladder, the floor, we would say. So then y is measuring the height of the ladder against the wall, right, as it slides down. What's a constant here? The ladder. It's not changing size, so so hopefully it's not a rubber, so it's staying 10 feet. Good. What's the implied variable? Or
Speed off the ladder to get the floor.
Time, speed, yes. So there's this hidden variable that we probably won't see when we try to explain this phenomenon with geometry, which is what we're going to need to do to set this thing up. But time is there. That's in fact, time is generally going to be involved in every rate, right? Because every rate, you think of as speed, it's going to be some linear measure over time. So and sometimes it's not part of the formula, but it's part of the story. So we're going to set up and what kind of a shape do you see there? Perfect. It's a triangle. So we're going to need to use, and what kind of a triangle? A right triangle. So right away we could start thinking Pythagorean Theorem. So a lot of these, that's what they're all set up with, right triangles, because good old Pythagorean Theorem is going to be very helpful. So let's get back here. So this is I'm going to kind of model how I would go about setting that situation up. So I copied at what rate is the height changing on the base of the ladder 6 feet from the wall. So it's moving out. So that's the whole thing of all these related rates, is we've got to set up some geometric equation on the situation, and then we're always given some specific time, place and time, or some part of the situation, and we get the related rate from there, because rates are changing, aren't they? Or at least they potentially could be changing. Now we were told that the rate of change for x is not that it's a constant. So there's another constant there. So let's see, what do I have here? So let's think through this setup process. Let's go back. Okay, so we've got this ladder. Yeah, we'll go like that. We'll call this 6 feet. We'll call this 10 feet. Might not be drawn to scale, but it's what I can do. What would the other side be? Just call it y. call it h if you want, the height of the ladder. Could we figure out what h or what y is at this point? Okay, so we could. We might need it at this point. So Pythagorean Theorem, right? This is the hypotenuse. So 10 squared minus the other leg squared is going to be equal to the unknown leg. And we'll take the square root of that, y squared. And it'll be the positive square root because it is a distance. So why don't we go ahead and do that at this time? So it's 100 minus 36, square root of that. Is that 64? Nice, isn't it? Because that's square root of 8. Yeah, square root of 64. So y is going to be equal to 8. Oops. And so what we've got is, we've gotten so far, the question is asking about 6 feet, that we've actually got a coordinate, 6, 8, so we've got an x and a y. And we kind of think about how we set that up. What would be the overall sort of general formula for this triangle that we could set up maybe in terms of x and y? Equals 10 squared or just 100. Good. So that's going to be our geometric equation. So that tells us wherever, once we know either x or y, we could find the other one. But that's the algebra of this triangle, of this moving triangle. Okay. We were told that, again, it's not in this part, but we were told in the applet, in the small part, if you read the fine print, that x is changing, that the change in x was 1 foot per second. Okay? So that's actually, so it's the rate of change. What is that? That's the derivative, right? And it's the derivative of x with respect to what? Time. So what we've got here, this is where we expand a little bit on our derivatives thinking. At what rate is the height changing? So what we're looking for when they're asking this is, we're really looking for what is dy dt. So what is the derivative of y with respect to time? They gave us the derivative of x with respect to time. So notice how we've kind of got this third variable now. We don't just have x and y. We've really got 3 variables. So as we take derivatives, right, because that's what we're wanting. We want a rate of change, which is a derivative. So we set up a geometric formula. We set up a function equation, and then we're going to use implicit differentiation to get its derivative. Okay. So what's the derivative of x squared? 2x. And what are we taking the derivative in respect to in this case? Time. So that is, we actually need a marker for this. Like I was talking yesterday, we just talked about needing a marker for y because our derivatives were in respect to x. But now we're taking it to that third variable. So we have to write this as this, oh, not dy, this is dx dt. We take the derivative of y. Let me make it prettier here. And what do we get? We get 2y, right? The 2 comes down, subtract 1, that's y to the 1 power, and this is going to be dy dt. Then we take the derivative of 100, that's my favorite part, 0. Okay, I know I'm always right on those. The other ones I can mess up on, but that one, constants are good. Okay. So now we've got the derivative. We've got to go back to our situation that we've got set up. We have a lot of this information. In fact, do we know what x is? Yes, they told us up here when x is 6. So we're going to put that in. Do we know what dx dt is? Yes, that was 1. They told us. And again, that's what all these problems are going to be. They're going to give you all this stuff. You might not see why they're giving it to us in the beginning, but this is why. We're going to basically need to know everything except for the one thing we're looking for. That's how math works. We need everything except for one thing. If we're missing 2 things, we can't really solve it, right? So then we have to add 2, and now this is where we might have gotten stuck because they didn't give us the y. And we sort of anticipated that we might need that, so we went ahead and found it. So that's another part. While they didn't give it to us, they gave us enough information that we could find it, and that's going to be part of the situation that comes up. dy dt, we don't know that. In fact, that's what we're looking for, right? So we'll put that there. And now we've got numbers for everything except for the one thing we're supposed to find. So now it's just algebra from here, right? Or, well, actually not even arithmetic, let's call it, okay? So 2 times 6 times 1, that's 12. 2 times 8, 16. This is always where I potentially will make my errors. Equals 0. I subtract 12 from both sides, so I'm going to move that over here. I get 16 dy dt equals negative 12. And again, I just kind of think I move it over, so it's going to become negative. And I start to see that my derivative is going to be negative. Doesn't that make sense? Because it's falling, it's going down, it's getting, that the height of the ladder is going down. And so then I divide both sides by 16. Cancels. And so my dy dt, if you reduce 4 goes into both of these, you get negative 3/4, or 0.75 feet per second. So at that point, it's actually going slower than the x. X is going at 1 foot per second. So it's slower. And what you can do now, when you were watching that, did it seem like it was sort of speeding up as the further down it got? And you could test it now, which I did. I went up a little bit higher, and it was slower. And as we got here, it does pick up speed, which is kind of weird, or at least I think it's weird, because x is constant. How can the base be at a constant speed while the top goes faster? Well, we see it. It happens. And I can't explain it, but if you're in physics, there's probably something that explains it, but it's how the world works. Okay, so far are we okay? So that's where we're going to use just implicit derivatives, differentiation to find the derivative, plug in all the stuff we know, we'll be able to find this other rate, which again, it's related, but it's different. The rate of change for y is different than the rate of change for x, even though it's got the ladder's constant, all this other stuff. And that's how we're going to go through these. Okay. Actually, this was my page. I was supposed to just set it up and then do all the work over here. But anyway, because I get feared that I'm not going to have enough room. I think I had enough room there. Okay, so that's kind of the idea. Set it up, write down what you do know, figure out what. Occasionally you get stuck if there's two unknowns. There must be a way to figure out one of them somehow. And again, sometimes it takes a little time, so we'll move it forward. So let's just take this one, which is not. I guess if you wanted to put a context to this, right? This is 3 variables, an x, y, and a z. Equals 9, and you see x squared plus y squared plus z squared. Does anyone know what that might be physically, geometrically? It's a sphere. Good. So it's a sphere of radius 3, actually. If it was just x squared plus y squared, it would be a circle of radius 3, but with the z variable. So it's a 3-dimensional sphere of radius 3. Or at least that's what it could be. I guess it could represent something else. But what they do is they tell us, okay, we've got this. They give us how x is changing, how y is changing. Let me close that off. And then we're supposed to find how z is changing. And again, we have to be given a particular point in time. So somehow maybe over time. So maybe this is the position of a ball. Maybe it's being inflated or something, but either whatever we know, X and Y are changing. Maybe it's a moving ball. Again, they didn't give us the situation, but some of this are nice because they gave us everything we need. We don't have to set it up, okay? So, what are we going to need? What do we have? Change in X. We've got the change in Y. What else do we have? We have X, we have Y, and we have Z at the instant that they occur. So what do we need to be able to solve this? The derivative. So we've got the function, and instead of rewriting it, I'm just going to write the derivative. So, and they sort of tell, I guess because again, it's implied the hidden variable here is time, so something is changing over time, right? So that there's this fourth variable in there. And so we take its derivative. So the derivative of x squared, just like we did last time, right, is going to be 2x dx dt, so the derivative of x with respect to t, plus 2y to the first power, derivative of y with respect to t, plus 2z, derivative of z with respect to time, and that all equals 9. 0, good. So that one I actually did on purpose. I just see if you're awake. So yes, we take its derivative, but sometimes don't you do that? You forget you're taking the derivative, you put 9 there, and then it messes everything up. So anyway, I do. So, okay, so now we've got our derivative. We see the z dt, which is what we're looking for, right? That's what the question says, find it. So again, if you want kind of the humor, I found it, I'm done, right? There it is. Okay. Yeah, do that on a test and say, okay, yeah, I found it, there it is. Okay. But what we have to do now is plug everything in, get the numbers, and actually find its value. So we start plugging things in. Here's x is 2, so I write 2 times 2. Dx dt, that's this one here, that's 5. And then I've got 2, and then y also happens to be 2 at this place. Dy dt, they gave that to us, was 4. And then we've got 2, and they give us z. Z is 1, so we plug that in. They don't give us dz dt, that's what we're trying to find. That all equals 0. And again, we'll do the arithmetic, move all the numbers over to the other side, and then divide by the number in front of dz dt. So in a sense, these become, once you get that derivative, you fill it up with all numbers. This actually, the algebra part is much easier than when we were doing implicit differentiation and we weren't plugging in numbers yet, because we had a lot of variables that had to get moved over, and it kind of looked, and we had to do some, right, we had to do some factoring, and it was, we don't have to do that today, so it's kind of cool. So 2 times 2 is 4 times 5, that's going to give us 20. 2 times 2 is 4 times 4 is 16. 2 times 1 is 2. And so we get 20 and 6, that's 36. So I'm going to move it to the other side. So it's going to become negative 36. And then I divide it by 2. So we find that dz dt is negative 18. So it's actually the rate is negative. Whatever's happening, z is getting smaller. X and y are getting bigger. Z is getting smaller. So and in case you know, this was number 9 from the textbook. that's another place you can pull up questions to work on. Pull up the odd ones like I did so that you can check your answer in the back. And so, like, you're in front of a class, you don't want to get embarrassed that you didn't know what you're doing, so you check the answer beforehand, and okay, so whatever. Actually, I worked on number 10 because I thought it was a good problem. I think I've got it in here, but then I couldn't check the answer, but sometimes that's okay. I thought I had the teacher's edition. They're supposed to give me all the answers, but they don't. So anyway, so far so good? Okay, so again, if they give us the function, just take its derivative, put in what we know, and we're going to be able to just solve for that one thing. Okay. So this is actually an example in the text, so you can, if you want to, you can follow step by step, but I thought it's also a good one for us to take a look at because there's a similar one in the homework that deals with this same shape, a cone. I think the cone in the problem in the WebWorks might be the other way around, but anyway, we've got a cone. So we've got a water tank that has the shape of an inverted cone, a circular cone, with a base radius of 2 meters and a height of 4 meters. If water is being pumped into the tank at a rate of 2 cubic meters per minute, find the rate at which the water level is rising when the water is 3 meters deep. Okay. So when they tell us that the rate of the water going in, what physical thing is that giving us? Well, what kind of a rate? What is that? The rate of what? That's your change in volume. Oh, good. Yeah, you said V. I didn't hear the V. So yes, exactly. The change is your change in volume. And so we got a little picture. So this is what we would draw. This is what the cone must look like. And we're given that it's got at the top a radius of 2 meters and a height of 4 meters. We'll put the meters in there. And so what do we need? Derivative of what? What equation? Okay, so of the volume of the inverted cone. So fortunately, we're given it, or we'd have to go look it up. Sometimes they just tell us these things, and if it's left that way, then you've got to go do a little research and find, well, what's the, how do I find the volume of an inverted cone? So those formulas are out there. What do you see might be a potential problem with this formula? It's got what? Multiplication. So that's a problem. But more than that, how many variables are there? There's a height, there's a radius, and there's volume. And then there's also time, because it's changing over time, right? So how are we going to do that? Well, we're going to cheat a little bit. Well, not really cheat, but that's why I wanted to set this one. Again, there's one like this in the homework. What we're going to do is we're going to take advantage that R and H, they're changing in relation, that they're similar to the larger cone. So as they change, they are similar to the larger cone. So what we're going to be able to do is solve for one of those variables, so we only have one of them to do. So we don't have to deal with R and H. We're going to get rid of them. And since we want the rate that the height, what's the question, right? The rate at the water level is rising, so that's a height thing, it's not the radius thing. What we're going to do is we're going to replace the radius with something for the height. So what we can do is we can take the radius over h is equal to 2 over 4. Oh wait, I want to solve for h. I could also do it the other way. I think that's going to be faster. Let's do h over r equals 2 over 4. 4 over 2, right? Because h is related to 4, r is related to 2. This is multiply both sides by r, and what you get is that h 4 divided by 2 is 2. Oops, h. Wait a minute. I always do this backwards. I want to leave h, so I have to solve for how r is related to h. I was right the first time I did this. So sometimes when I do these, notice I would have got h equals 2r. If I replace that, then h is gone, and I can't answer my question about how is h changing, right? Because it's gone. So what I started off right here. I'm going to multiply both sides by h. Notice I get kind of the same answer, I guess. I think this is how I want to do it. So the h cancels. R is equal to 1/2 h, or h over 2. Let's write it that way. Okay. And I didn't realize it until I was coming back when I got it solved, and I replaced it here. Oh, I only have r. There's no, yes.
Wait, is that derived from the volume equation?
It's derived from that the cone is similar because a smaller cone, because of the geometry of the cone.
Okay.
And they don't really explain that. They just throw it out there and say you do that. And I said, okay, because I also teach geometry. I said, how could they do that?
So where does the v go?
Oh, the v's over here. So we're still going to do. What we're doing though is we took advantage that it's similar, so that we can then get it down to just fewer variables. Because otherwise, we're going to have a dr dt, and we don't know how that's changing. We might be able to do it that way, but what we're going to do is we're going to take v is 1/3. We're going to replace r squared with this, so it's going to become h over 2 squared times h. Okay, so notice we don't have to worry about that r. So there's sometimes it's just like and they didn't give us enough information to really work with it. Okay. And it takes advantage that, yeah, as h change, r changes proportionally because they're similar, the two similar. Okay, so then this becomes, let's see, we're going to square that. Okay, v equals 1/3 pi, which is all a constant. We're going to get h squared times h, so that's going to be h cubed over 2. If you want, I kind of like, we can, oh, thank you. I was going to leave it as 2, and that's another mistake I could make, right? Because 2 squared, that's 4. And then, if you want, you could take 3 times 4 and make that 12. I'm just going to do that, so I'm going to do this as pi over 12. So my constant term is just there. I don't have to worry about it. It's less messy. And then I've got h to the 3rd. Okay. Let's see. So now we could take implicit derivative, right? dv. So on the left-hand side, the derivative of the volume, that's our dv dt. We get our constant, pi over 12. Derivative of h cubed, 3h squared dh dt. So far, are we okay? Yes?
Why don't you take the derivative of the constant?
Because we're multiplying. So that's, if it was adding a constant, we take its derivative, it becomes 0. But when it's multiplied, it just tags along for the ride. Good question. Thank you. Yeah. And so, we can reduce this 3 and 12, so we're going to have pi over 4 there. Let's rewrite it. dv dt is equal now to pi over 4 times h squared times dh dt. And now's the point where we should hopefully have all this other information. They give us the rate of the volume, which you mentioned. This is dv dt here, because that's water being pumped in, so the volume of the water is changing. We have 3 meters deep, so that's the height of the water. That's the h, so that's the time when h equals 3, so we can plug that in. And then the only thing that's not known is the h dt, and that's the question, is how quickly is the height changing? So, you know, kind of, and what would you expect it to do as it fills up? Will it speed up or slow down? Slow down, because that radius is getting bigger, right? So, you know, the first part fills up real quick, the height changes quicker, but as we get closer to the top, it's slowing down. But you might need to do this if you're trying to get a shut-off valve of when to stop it, you know, how fast is it going and that kind of stuff. So we go ahead and fill this stuff. So right, dv dt is 2, and you could use units here, but everything will pretty much cancel out. We'll get up, and this is pi over 4. H is 3, so that's going to be 3 squared, right, which gives us 9, and then there's the h dt. So we've got 9 pi over 4. We multiply by the reciprocal. So I'm going to rewrite this as 9 pi over 4 times dh dt. And so dh dt, multiplying by the reciprocal, is going to be 4 times, let's do it this way, 2 times 4 over 9 pi, which is 8 over 9 pi. What's that? Well, that's why, yeah. So that's why I wanted, because even though they have it written out, and you can read this in how the text says it, but they gave us this, and they didn't explain it, but they just said, okay, they were the ones that said solve for R or H to get it down to 2 variables. Yeah. So that's what you're going to see. Is the struggle with this is they're throwing us some problem-solving loops. And those are hardest ones to teach, because this one we have to do that, this one we have to do that, and it's hard to just spot it. When we're going over techniques of how to take a derivative, that's pretty straightforward. Bring this down and do this. I can show you those techniques. Problem solving is more of an art form. And again, you only learn by experience. You learn by making mistakes. And so that's, you have to have a willingness to make mistakes. In fact, actually, I finally, as further along I went, not only was I willing to make mistakes, I was looking forward to them, because I knew those things would be my best lessons. I didn't really look forward to them, but I knew I would learn from them, but yeah, they're hard. Okay, so far we're doing okay. And some of them are going to be a little bit challenging. Again, those are the ones you're going to want to skip over. Some of them will just be already set up, and okay, just do the implicit derivative, plug in all the numbers, and you're done pretty quick and easy. So those will get you some practice. There's a couple in there. There's one with the same one with the inverted cone. There is one on the sphere, but the sphere we sort of did one, and like I said, there's another example. That one's actually not too bad. Because of the equation of a sphere is a lot easier to work with. But that one was tricky, okay? So I thought I'd throw this one in. Where did I get this one? I think this is also out of the text. But I wanted to do this because it has a product rule in here using implicit derivatives. So that's the tricky part. Even though it's kind of, the equation doesn't look too bad, but you have to think through that we're going to have to do a product rule here. So we've got some particle moving along. Is that a hyperbola or a hyperbola? I'm not sure which one. I would say a hyperbola, but that's probably hyperbola. Anyway, that shape. And then we've given a point that it's going to reach, so we're given an x and a y coordinate, or the coordinates x and y, right, ordered pair. We're told that the y-coordinate is decreasing at a rate of 3, so that's cool. They're giving us one of the derivatives, which is always necessary. And then they want to know how fast the x-coordinate is changing, so we need to know dx dt, right? So that's the question. So the question mark is, what is dx dt? They're giving us here dy dt equals 3. Now sometimes they could have just given us the x and then we would have had to solve for y, but it's kind of nice they gave us both so we don't have to. But some of the equations, they only give you the x or they only give you the y, so you have to go back to the original equation and figure it out. But since they give us both, really all we need to do at this point is differentiate it using implicit derivatives. So we're going to take the derivative of x, and what are we going to get? Derivative of x is 1, right? So derivative of x is, I'll write that 1, dx dt times y. Nothing, and we're not taking the derivative of y yet. Remember, that's the product rule. The derivative of the first one times the second one unchanged. Okay. And then what do we do? Plus, there's this plus, and then we're going to take the derivative of y with x unchanged, right? So then we get x, and then y, I'm going to put 1 to emphasize that I took the derivative of y, which is just 1, and then that's going to be dy dt. And then my other side, favorite derivative of 8, which is a constant, this one is 0. Because it's not multiplied by a variable, so it doesn't tag along, it's gone. So far we're good? But that's, again, it's just a little trickiness because of the product rule. If they throw ones in, there's some examples in the book with trig functions. I don't remember there being one in the homework, but there might have been trig functions. We might also have to look at the chain rule because it has an insight. So see about those. So anyway, now we can start plugging things in. What is dx dt? Well, that's what we're looking for, so that stays. What is y? That's 2, so we plug that in. What is x? That's 4, so we can plug that in. 1 is still 1, so we multiply. And then what's dy dt? It's 3. Thank you. It's decreasing, so we have to watch our signs. And again, this is one thing I said, oh, it's just 3, right? Because you look too quick. But look for the words, it's decreasing, because otherwise you're not going to, your answers aren't going to match, or, you say, I did everything right, but again, you forgot about the negative. And again, it wasn't shown there. And all that equals 0. So we get 2 dx dt minus 12 equals 0. So we add 12 to both sides. Positive 12. And then we divide by 2, right? So this cancels there. So that dx dt is 6. And it's a positive 6, so x is increasing as y decreases. And doesn't that make sense that if we're going to multiply two numbers and they're going to be equal to 8, as one gets bigger, the other has to get smaller, so that they get this constant of 8. So it makes sense, I guess, if you think about it. A little more straightforward. We didn't have to draw the pictures instead of the geometry and such, but. So that's, again, we're just going to do implicit differentiation. There's 8 problems. Let's see, I think we're almost, and that's all the examples I had. There's going to be one on the sphere. Again, I'm going to direct you to take a look at that 4-minute video. He walks you through pretty quick, although we kind of did one. But it's in the text, they have these step-by-step. You might need to draw some pictures. You might need to look up some formulas for geometry. It's basically, we have all the information except for one unknown, take its derivative, fill in the stuff, and that's what we do here. Okay. Awesome.